Okay, so Jamie's talk, surface impact dynamics, exploring the stick to bounce transition.
Cool. Yes. So this is my talk on Miclauchlan.
Jack, are you on? You're just on the focus button.
Yeah. Hello. Yes. Welcome to my talk. I will be looking at microdroplet impacts as they impact solid surfaces, and looking whether they stick or bounce. And this will be mainly done through the experiments, also simulations, and some analytical models. So let's just jump straight in with a question. There. Oh, yes. Here is our first question. So when do droplets of any size bounce off a solid surface? Well, there's kind of two main special cases that are very well studied. The first is on non-wetting substances. So this is substances that don't like to be wetted. And droplets should always bounce off these surfaces unless they're too viscous or they're too large. And that's stated in this kind of limiting case here. The Ornith-Sorga plus bond number equals 1, where our Ornith-Sorga number is something that scales with viscosity, and our bond number is gravity versus surface tension. Of course, our wrong way. Of course, microdroplets can never be too big. So the only limiting case for microdroplets to stop bouncing should be the viscosity, assuming it's this ideal surface. The other mechanism that's very well understood is so-called contact bouncing. And this is where a droplet impacts the surface at a very specific range of velocities, such that there's an air film that forms between the droplet and the surface. And rather than being in contact with this surface, it spreads on this air film. And it's been observed for millimeter-sized droplets, but this film there is nanometers in size. It's never been seen for micron-sized droplets. So it's a bit of an unknown. But as I say, it's a very special case for very specific impact velocities. But more generally, it's kind of not understood how surface interactions affect where we have bouncing. So we know we get sticking, we get bouncing, but other than these two special cases, not a lot is understood. So what do we need to know to be able to consider this problem? Well, we need to think of all the variables at play. We have things to do with our surface and things to do with our fluid. For our surface, we have interfacial energy, we have roughness, we have geometry, and we have interactions with the fluid. And the fluid has inertia, surface tension, viscosity, etc. Now, to simplify the problem, we want to rule out a few things. For kind of a generic looking at bouncing and sticking, we want to just consider a flat surface, ignore any chemistry that goes on between the fluid and the substrate, and we want our fluid to be ideal, i.e. have Newtonian properties. And if that's the case, then we can quantify all our surface properties simply in terms of contact angle, theta of the fluid makes with the surface, where in our ideal non-wetting condition, theta is 180. And this can be dynamic, so this contact angle could change, or it can be static as we have the fluid on the surface. And for our droplet's physical properties, we can categorize them by two key dimensionless numbers, one of which I've already mentioned, the Ornith-Sorga number, which is the ratio of viscous force to inertia and surface tension, and the Weber number, the ratio of inertia to surface tension. Very roughly, think of this top one as being associated with viscosity, it's where that limit comes from, and the bottom one with impact velocity. So these are all three key variables that we can look to see if we get sticking or bouncing. So how do we carry out an experiment to see this? Well, thankfully, at the University of Bristol, Jonathan Reed's PhD, former PhD student Lauren McLauchlan, built a great certificate for looking at surface impact dynamics. And it involves a high frame rate camera with a lens that you can focus on really small droplets on, a motor which is attached to a surface which you can move, and a piezoelectric droplet generator allowing you to image droplets moving really fast, hitting a surface. And for looking at bouncing, I chose the surface of Teflon, which is a static contact angle of 108 degrees. So it's hydrophobic, but not completely non-wetting. And I used water and glycerol, so we kept the surface tension constant, but allowed, and also allowed our contact angle to be constant, while varying the viscosity and the velocity. And from doing that, we got videos like this. If it plays. Yes. So what we see here is we see a droplet impacting at around 6 meters per second, and we see it hit the surface, spread, retract, and then bounce off, but not just a complete rebound, we actually get a small little sessile droplet as well. And this, we can note down our Weber and Onasauga number for this, and we can then change those and see what different outcomes we get. And the other outcome we got, which shouldn't be surprising, is sticking. As you can see here, we have a droplet impact, spread, retract, do some oscillations. And the thing that changed between us, our droplet bouncing and our droplet sticking, is it's now going slower. But note, the Onasauga number is still much below 1, so if this was an ideal non-wetting surface, we'd expect this to still bounce. So we repeated this experiment lots and lots of times, and got a diagram like this, where all the red points you see are bouncing, all the green points are sticking, and you can imagine drawing some sort of line in this diagram, and kind of treating these like two different phases. This is like a phase diagram, where you're transitioning between the two. You go from stick to bounce if we increase the Weber number or velocity, and we go from bounce to stick by increasing the viscosity. Of course, this is just for Teflons. We wanted to verify this worked for other surfaces. So we also bounce things off a silicon nanoparticle coated surface. We got much more prominent bouncing, and importantly, we also got Weber dependence. So we had this experimental result that we could see Weber and Onasauga dependence on our bouncing, and we still have the same partial rebound dynamic with the small sessile part. So to further our understanding, we then decided to do some simulations. So we did phase field simulations in COMSOL, looking at 40 micron water droplets impacting a wetted wall with the same static contact angle as Teflon. And for this Weber number here, which would be this on the experimental diagram, we got sticking. And as we increase the impact velocity, we moved to bouncing, which is good. So there was some rough alignment between our experiments and our numerics, namely that we saw Weber dependence, and this was from this surface quantity. And if you look at the image, the left being the experiment, the right being the numerics, we had similar dynamics, and there was no air film when we got this bouncing, i.e. this bouncing was due to being in contact with the surface, not to being at a very specific range of velocities. There were some issues though, namely we don't get the satellite droplet when we have this bouncing that we saw in the experiment, possibly because we don't have contact angle hysteresis or roughness in this simulation, and it's quite dependent on mobility, so it still needs some refinement. But what we thought from this is, can we take the basic physics that we see in this and apply it to a much simpler model? So one thing we can see in the simulations and the experiments is the droplet is kind of in two parts. One part associated with the surface here, and one part heading upwards. Just so happens in the experiment that part sticks, and in numerics it goes up. And what we said was we could make a ball and spring model from this, where we consider this droplet to be two separate parts, the top mass and the bottom mass. The bottom mass being attached to a surface via a spring, which represents the surface interaction, and these two masses being connected by a spring, representing the surface tension, wanting to restore the droplet together, and then some sort of viscous dash pot to represent the viscous dissipation in the system. And from this, we can write out some second-order differential equations and non-dimensionalize them in terms of our Weber number and Onasauga number, some dimensionless masses and a Weber number associated with this. And from this, we can see how the system oscillates. So it oscillates something like this for a specific Weber and Onasauga number. And what we could say is that if this top mass gets a certain distance away from the second mass, we have bouncing. And if they stay close together, we get sticking. So we could do this oscillation for thousands of times and see how this mass separation changes. And if that happened, and we did that, and we get a very complicated graph looking like this, where this y-axis is how far apart the droplets got, and the x-axis is the Onasauga number, and changing color is the Weber number. And what we can see is we transitioned from this really far apart bouncing stage to our sticking stage as we increase the Onasauga number, like in the experiments, and we transition from the stick to the bounce, like we saw in the experiments, and we increase the Weber number. So we could draw on some arbitrary transition here and say everything up here is a bounce, everything down here is a stick. Of course, this is just a model. The phase transitions are quite thick in Onasauga. It's not one-to-one between experiment and reality. There'll be some sort of scaling. But it's a nice little toy model to play with. And if you draw where this transition line is, you get a nice linear fit. But the key point is we've managed to replicate the same behavior from considering the droplet as two parts and one part that is associated with the surface. Can we further this? Well, what we can say is that our little toy model captures all the complicated physics that we want to ignore. So the spreading, the retraction, how it interacts with the surface, and simply the initial Weber and Onasauga number pick the outcome. Either it sticks or splits into two parts and bounces, be it really does that or it does just kind of theoretically split into that. At the cusp of bouncing, so where we're just going from this part to this part, it must be true that the upward kinetic energy of the top droplet must tend to zero. I.e., we can then do an energy balance between the initial kinetic energy, surface energies, all the viscous dissipation, and we can set that equal to each other. And if that's the case, we can actually derive a Weber number for this bouncing condition. And we did that. And we got this condition here, that the Weber number of this transition from sticking to bouncing is equal to a constant, which is dependent on static contact angle, divided by 1 minus the Anasorga number, times a small correction factor if the surface is rough, or an atypical contact angle hysteresis. And let's look at this closer. What we can see is that this acts asymptotically as Anasorga tends to 1. So we still have our limit from the non-wetting surface that it can't be too viscous. I.e., it doesn't matter how fast you hit the surface, once you're past this limit, you will never bounce. If you do a small expansion for a small Anasorga number, you'll see this will act linearly, so it'll look like a straight line, just like we got in our experiments. Which means if we ignore our prefactors, we can write an ideal condition to bounce, that our Weber number times 1 minus our Anasorga number has got to be greater than some constant dictated to by the contact angle. And if you graph it, it looks something like this, where you have your bounce, your stick area, and as you increase this function here, depending on the angle, it looks something like this. So, in summary, we've come up with this new kind of contact bouncing condition that's particularly applicable for microdroplets, dependent on Weber, the Weber number, the Anasorga number, and our contact angle. And we recover our Anasorga equals 1 limit from it, which is good. And we do need to do further works in numerics to refine it and compare it to this model. But you can see all kinds of applications for aerosol impacts, looking at bouncing, say, for respiratory droplets on face shields. And if we wanted to complicate this even further, we could look at some non-Newtonian elements to this. But yeah, that's it for me. So I just want to acknowledge my supervisors, my funders, and everyone else who helped along the way. And I open the room to questions. Thank you very much.
Thanks very much, Jamie. Do we have any questions? Right at the back. Richard, right at the back, very forward.
Lovely talk. When you see a sensile drop,
Yes.
detaching, is it like a really plateauability that thing stretches so much?
Yeah. So,
like a...
yeah. So you have kind of like necking where it happens, and you have this pinch back of the small droplet. Yeah.
Had a question down the front there, Bonnie.
That's very interesting. The usual problem with the energy models is that there's a fudge factor
Yes.
to do with the viscosity and the energy dissipation.
Yes.
So can you say a little bit about how you dealt with that?
So what we've done is we've scaled our viscous dissipation with a fudge factor and the time scale it will be in contact with the surface, which is actually independent of how fast it hits. It's purely material property in terms of its surface tension and density.
Do you try and get that from a rectangular dissipation?
Yeah. It's very kind of fudge factory. Yes,
There's quite a bit of evidence, quite a lot of data looking at bounce in impactors.
Yeah.
Obviously, those are much smaller particles. Have you tried extending your understanding to just see if you're consistent with a much smaller size region?
Not yet. No, we've purely been looking at what we have, and obviously we can't always compare it to larger droplets because our bond number is negligible, and for larger droplets it isn't. So that's that. But looking downwards, I don't see why it shouldn't not fit, because the dimensionless numbers, as I say, scale whichever way you go. So it should be able to. We've not done yet.
Thanks very much, Jamie.